right? So if you recall, we saw the the adversarial indistinguishability experiment, and I had defined what it means to be perfectly indistinguishable, right? So it's perfectly indistinguishable if for every adversary A, the probability with which A succeeds in this experiment is exactly half. Okay, and then we wanted to work with an example, right? So we considered this visionaire cipher. So this is the encryption scheme that we are considering, with key length to be either 1 or 2, and 1 or 2 is chosen uniformly. And then the message space is a set of 2 character strings. And for this adversary that I had defined, we want to compute the probability priv k av a comma pi is 1. Okay, so you recall the question? Did anybody already finish it? Okay, so right, so as I mentioned, in order to compute this probability, right, we can essentially compute the probability with which A succeeds when B equal to 0 and the probability with which A succeeds when B equal to 1, and then sort of split this into these two terms, right. So this is something that follows by basic laws of probability. So right, so we write this as probability priv k av a comma pi is 1 condition on B equals 0 times probability B is 0 plus this term times probability B equals 1. So what is the probability that B equals 0? When you say, so half, right? So let's talk in those numbers just to be sort of uniform. So is that what somebody else wanted to say as well? So why is it half? Yeah. No, if it's only two, yeah, exactly, uniformly distributed, right? So it's not just because there are only 2 options, it's that the bit B is chosen uniformly from these 2 options, right? So because bit B is chosen uniformly from those 2 options, the probability B is 0 is half, and so is the probability that B is 1. Right, so let me maybe give myself more space and I will write it here. Right, so in this example, continuing with the example, we want probability priv k av a comma pi is 1 for that A and that pi, and we just saw that we can write this as half times probability priv k eav a comma pi is 1 condition on B equals 0 plus half times probability priv k eav a comma pi is 1 condition on B equals 1. Okay, so what is actually, is there a question? Right, so when we say priv k av a comma pi is 1, what is the definition here? So when does the experiment output 1? No, that is when the adversary A outputs 1. So when does the experiment output 1 is the question. So when is priv k av a comma pi 1? When the adversary's prediction is correct. So essentially when B prime equals B, right? So what would that be in this setting? What should B prime be in this setting for priv k av a comma pi to be 1? It should be 0, right? So essentially the output of the experiment is 1 if B prime equals B. So essentially when the adversaries guess B prime equal to B. So essentially here when B is 0, this essentially means that probability with which A outputs B prime equals 0 condition on B equals 0 plus here again the experiment will output 1 when B prime equals B. So essentially A outputs B prime as 1 when B is 1. So that is when the experiment will output 1. So is this step fine with everybody? Yeah. Why is it the question? You understand? Okay. Yeah. Right, so the experiment outputs 1 when B prime equals B. So if the experiment is outputting 1 here, then it's essentially A outputting 0 when B is 0 and A outputting 1 when B is 1. Right, so this is by definition of the experiment. Okay, so we are all, it's all clear so far? Okay, so now, so again, it looks like I have to keep this board, so I will move here, unfortunately. So now I want us to compute, say this probability, right? So what is the probability A outputs 0 condition on B equals 0? So maybe take a minute to think about it. Okay, so we know the A we are considering. The A we are considering follows this strategy. Okay, and B equal to 0 implies which among these two messages is getting encrypted? M0. So essentially B equals 0 implies that M0 is getting encrypted. Okay, so now what is the probability under which A outputs 0 when M0 is getting encrypted? So you can think about it for a minute. Yes, we should, right? Because that's the key generation algorithm. Right, so essentially A output 0 condition on B equal to 0, how do you analyze that? So think about it for a minute and then we can discuss. Yeah.
To basically know the answer for that, we need to know what C1 and C2 is.
So it is not that, so essentially, right, when M0 is AA, there are various possibilities for the key and various possibilities for that C1 and C2. And so depending on those various possibilities for that C1 and C2, there will be a probability with which A will output 0. So if you know precisely what C1 and C2 is, you know precisely what the output will be. Yeah.
So because we're using the linear cipher, one of the only ways that C1 can be equal to C2 is if the key itself has the same digit being repeated.
So there are two possibilities for the key length. So you're talking about the case when key length is 2?
Yes, because if it's with length 1 and the period is 1, it will be repeated.
Okay.
So for the second case, it is when both the letters are basically the same in the key. And so if that then depends on our message space.
So essentially, how will you compute this probability? So the thinking is right.
So then again, we have two conditions. One is if the key length is 1.
So the key length is 1 with probability half, right? So
times, then every time C1 will be equal to C2
Uh-huh.
because we're using the linear cipher. So that's a 1
right.
plus another half. And then
So this is for key length equals 2.
2.
Okay.
And because you're choosing 1 out of 26 letters basically, so it's 26 C1 twice.
Okay. It's just 26 C1 twice?
Square. Because again, it's 1 in 26 chance and then a 1 in 26 chance is choosing the same thing again.
So essentially for the first you have
For the first we have, like, let's assume C1 and C2 are both A. So the chance of choosing A first is 1 in 26. And then the chance of choosing A once again is 1 in 26 again. So it's 1 over 26 squared.
see, but essentially, right, it is not just A. So it is when C1 equals C2. So the thinking is correct, but the computation, sorry? Half into half? Is it half? no, it's not just two possibilities, right? So for instance, if you choose one, so let's say the characters of the key are K1, K2, okay? So you have 26 possibilities for K1, but once you fix the 26 possibilities for K1, your possibility for K2 is fixed. So what would that be? 1 into 1 by 26, right? So essentially this would be 1 over 26, right? So essentially, so what is the reasoning here? When does A output 0? A output 0 by our definition of the adversary when C1 equals C2, okay? And now we are considering the message corresponding to B equal to 0, which is M0, right? So when M0 is AA, so AA will be encrypted to some C1 and C2 such that they are equal in only two cases. Either the key length itself is 1, so then both of these were encrypted by sort of the same key, K1, K1 to result in some ciphertext that will essentially be some C1, C1, right? Or, so this is corresponding to this, or the key length was 2 such that K1 equals K2, and again they have resulted in the ciphertext pair C1 equal to ciphertext with two characters C1, C2 such that they are equal, right? And this is the probability of that. Okay, so this is how we are computing probability A output 0 condition on B equal to 0. Okay, so similarly, so I hope this is clear. So similarly, can you think about how would you compute probability A outputs 1 condition on B equals 1. Okay, so this is this part of the computation. What about this part? So I want everybody to think about it. So you can try it on your own and then tell me.
I still think it's 1 over 26 squared. Half into 1 over 26 squared.
Here?
Yeah.
So I think I could be wrong, but I think based on how you're reasoning about it, I think you're fixing the key K to be key K, for instance K1 to be a particular letter, but it could be any letter of the.
Yeah, that's why 1 over 26 for K1 there
Yeah.
are 26 possible choices and we can choose any one choice. Let that choice be X.
Okay.
For K2 you have to choose that same X again.
Yeah.
So again there are 26
So
possible
yeah,
choices
so
and you have to choose one of them.
yeah, but in your first K1, it could be any of the 26. So it could be it is 26 over 26 times 1 over 26, right? So K1 essentially allows you to choose any of the 26 possibilities, whereas K2 fixes that it should be K1. Okay, so essentially in your computation of 1 over 26 square, you fixed K1. So essentially you have to multiply it again by 26. Exactly, exactly, exactly. So any thoughts on how you would proceed for probability A outputs 1, condition on B is 1? You had an answer? Yeah. So why is it 0 here?
Because whatever character we select, it will be same. If you select one for first digit, if you are choosing one digit, if you choose A, then second letter will again be A.
Exactly, because so now since B is 1, we are encrypting M1 equals AB, right? So an AB have differing characters, the plain text has differing characters. So when, in the case when the key length is 1, so which is sort of the first term, it will always be K1, K1, which will result in C1 not equal to C2 because A not equal to B, right? So, in the case where, oh sorry, actually I think we are computing something else, right? You're computing this.
No, it's A output 1
Sorry?
given B equal to 1. A needs to output 1, that is when
But then this is not 0, right? So then it's half into 1.
It's 0, it's 0.
So wait, one of you answer so that I can follow the thinking of one of you. So I'll come to you in a second. So if the ciphertext were not equal, A will output 1.
I was taking M0 itself.
No, so right, so that's where the mistake is, right? Because B is 1, we are encrypting M1. Okay, so maybe that's what you were doing as well. Okay, right. So, so just to re-establish, because I don't know if the discussion was confusing, when B is 1, we are encrypting the message M1, right? So when I say we, the experiment, right? So the experiment when B is 1 encrypts M sub B, which is M1. Okay, so actually it is in fact easier to compute probability A outputs 1 condition on B equals 1 as 1 minus probability A outputs 0 condition on B equals 1. Although that it's not what you intended to do, this is in fact easier to work with. So here, right, so A will output 0 only when C1 equal to C2. And in the case where C1 equal to in the case where M1 is encrypted, to your point, since it's the same character of the key that is repeated and the plain text is such that the characters are not repeated, C1 will never be equal to C2. Okay, so here in the case where the key length is 1, A will never output
Isn't there one case where it can?
when the key is of length 1.
No.
Yeah, when the key is of length 1, it can never do that because the keys are repeated and the plain text characters are not repeated, right? But what about the case when the key length is 2? 1 by 676. So how did you come to that calculation? So it's half into, so key length is 2 is probability half. Is it only one combination? So what is the combination you're thinking of? Sorry? Can it only be BA? So why BA? So essentially BA because you want C1 equal to C2. So you're essentially using K1 plus 1 and K2, right? Exactly, right? So then what is the answer? Very similar to this, right? So is this, sorry, just to sort of rewind the discussion, so when B equal to 1, that is when AB is encrypted, when the key length is 1, C1 can never be equal to C2, right? Because the key characters are the same, the plain text characters are not. How about when the key length is 2? So essentially AB is encrypted and you have keys K1 and K2. When can C1 be equal to C2? Sorry? It's okay, you can be wrong, it's fine, go on. So I'll come to you, I think you already. So when it was AA, it was clear, K1 and K2 needed to be equal. When it's AB, is there any possibility for K1 and K2 such that C1 can be equal to C2? Yeah.
Just BA
Okay, BA, that's all?
First character is greater than the second character by 1.
Exactly, right? So that's exactly right. So BA satisfies with property, and I guess that's what you are going to say as well. So essentially, if the first character of the key is greater than the second character by 1, right? So essentially, you know, you now correct, yeah. So right, so essentially it's not just BA but really anything that satisfies this property, because now if you see A will be shifted by K2 plus 1 times, whereas B will be shifted by K2 times, and since B is 1 more than A, this would result in the same ciphertext, right? So again, similar to our previous calculation, you can choose any character for the first for K1, and that would fix the second character, right? So similarly again, you will have this to be 1 over 26, okay? So is the computation clear? So I mean, there might be mathematically doubts as to how we arrived at the expression, but at least is the thinking clear first, and then we can clarify mathematical questions. So any questions? Okay, so you can think about this offline, and really the purpose of this exercise is so that we understand the definition, right? So we understand exactly how we take part in the experiment and compute these probabilities. Okay, so now we have these two, right? So this is 1 minus, right? So putting this together here, we have half plus half times 1 over 26 plus 1 minus, so half times 0 is just 0, half times 1 over 26. Okay, so times half, right? Because it's half times probability A outputs 0, condition on B equals 0, plus half times A outputs 1, condition on B equals 1. So now actually you will see that this and this will get cancelled, and finally you will have 1 over 4 plus 1 over 2. Okay, so this is how sort of mathematically it would come out to. So what does this imply? This computation? It's insecure, right? So insecure according to, so this definition that we saw, right? So what this implies is this scheme that we considered is not perfectly indistinguishable, right? So it would be, for it to be perfectly indistinguishable, only if this was equal to half, right? So exactly right. So essentially all this computation to see that there exists an adversary for which probability priv k AVA comma pi is 1 is greater than half, so the scheme is not perfectly indistinguishable. Okay, so maybe one thing I will try, actually, you know, like I'll write my email address here, so you can write to me, right? So it's my name at csc.iitm.ac.in. Okay, so what I would like you to try, sort of like, you know, at the end of today, is consider, okay, so we define this adversary A, okay. So now consider another adversary that outputs M0AA and M1BB. Actually, maybe I'll already ask you, what do you think the computation would come to in that case? So essentially the question is the following. In this example, we considered, so let me erase sort of the extra bits. In the example, we considered M0AA and M1AB. I am now defining another adversary A prime, where I am defining M1 as BB. Yeah? Thinking, okay. So maybe I'll let you think about it for a minute already, and I will take guesses. For this question, I will not, it's okay if I don't get a perfect answer, but for the sake of discussion, it will be useful. It will be exactly half.
So it's the same. M0 and M1 are essentially.
Yeah, so you can check it, but you're right. Actually, for this adversary A prime, so prove K EAV A prime comma pi, the probability of this would actually be exactly half. You are right. So you can, you know, the guess might have been, yeah. So just check the computations of it. So now let me ask the question. What does this imply? What does this figure tell us? Yeah.
Basically, in this experiment, the adversary has to be smart enough to not choose messages that will give it the exact same information regardless of which other message is in.
Good. Okay. Can somebody add to that answer? It is perfectly indistinguishable, you're saying? But that's not exactly adding to that answer. So, right, so this is exactly why I asked the question, which is, so when it was 0.75 and greater than half, we could immediately conclude that the scheme was not perfectly indistinguishable. But when it is equal to half, it is for the specific A prime, and sort of your answer was that, you know, adversary needs to be smarter. So in some sense that is true, and actually the fact that this is half does not imply that the scheme is perfectly indistinguishable, because if you recall, unfortunately I don't have it on the board anymore, for perfect indistinguishability to hold, it needs to hold for every adversary A. All this computation has told us is there is an adversary A prime for which it is half. But we just saw an adversary A for which it was 0.75, the same scheme. So pi did not change, right? So the scheme is still not perfectly indistinguishable. So this computation does not really tell us anything apart from maybe we need to like come up with smarter adversaries, right? So it is important that the definition holds for every class of adversary that we are considering. So the definition says that a scheme is perfectly indistinguishable if for every adversary A, the probability with which priv k AV A comma pi is 1 is half, not just for a single adversary, right? So there could be, for instance, this A prime could have just said output 0 with probability half and 1 otherwise, right? So that adversary will again be successful with probability half, but that's not an adversary that is really doing anything with the ciphertext that it's observing. Okay, so I just wanted to make that point clear. So is the definition and sort of how we work with it making sense? Any questions? Okay, so then what I will do, so we'll sort of like look at, you know, we are still somewhat in the classical setting, okay, and the reason is the following. So as I mentioned, perfect secrecy is equivalent to perfect indistinguishability, that the definition that we saw, but there are some limitations of perfect secrecy, okay. So for instance, right, let's go back to the one-time pad. Right, so I mentioned, I didn't prove it, that the one-time pad is perfectly secret. Okay, and maybe you discussed this yesterday already, but there is a reason that the one-time pad has sort of the prefix one time in its name. Why is that? So essentially, right, so if the sender sends m XOR k or m1 XOR k to the receiver, right, so this is the encryption under the one-time pad, and then first sends this and then sends C2 equal to m2 XOR k to the receiver. So this is sort of a second ciphertext that it's observing. One can compute C1 XOR C2 as m1 XOR k XOR m2 XOR k equal to m1 XOR m2, right. So essentially this will already tell us exactly which bits differ in m1 and m2, right? So when the bits in M1 and M2 differ, M1 XOR M2's bit would be 1, right? And when they don't differ, it would be 0, right? So by the property of XOR. So it's already telling us something about the underlying message, and in that sense it's not perfectly secret, right? So the one-time pad is perfectly secret essentially only when the key K is used to encrypt exactly one message. Okay, so the moment you encrypt more than use the encryption algorithm more than once or use the key to encrypt more than once, we lose perfect secrecy. Okay, and so this is sort of a limitation of perfect secrecy, and it is not true just of the one-time pad but of any perfectly secret encryption scheme. So one-time pad is just an example. Okay, so and ideally, when we are out there in the world, we want to use the same key multiple times to encrypt messages, right? So we don't want to be restricted to be using it only once. Okay, so this is one limitation. So another, so I'm not writing it out formally. I encourage you to take a look later. Right, so use only once. And the other limitation that is again inherent to perfect secrecy and exhibited by the one-time pad is, if you recall, in the one-time pad, the message length and the key length had to be the same. Okay, by definition, if you are encrypting messages of length L, you used keys of length L in the one-time pad. And again, like just inherent to again, when we want to sort of use encryption schemes out there in the real world, say the key could just be 256 bits, but we want to be encrypting large files, right, not just 256 bit messages. So one-time pad is not actually what is used, and essentially this inherent limitation of the key space being as large as the message space is inherent not just to the one-time pad but to the perfect secrecy setting. So for this reason as well, even though one-time pad satisfies this notion of security, perfect secrecy that we saw that seemed meaningful to us, this security definition is too strong for us to actually use practically. So we need to actually weaken this definition, and in particular we will weaken it in two ways. One, in that, so we required security to hold for every adversary A, so we did not place any computational limits. And to your answers in the beginning of the lecture, we will actually place some computational limits and talk about only some attackers that work within these computational limits, and security only against those attackers. And apart from that, another meaningful weakening that we will see is, instead of requiring, say for instance here, so I erased it, but probability with which the adversary succeeds in the experiment is exactly half, we might allow the adversary some small probability of success, more than half. So maybe it's half plus some negligible amount, and we are okay, we will live with it. Okay, and so essentially we have to define exactly what is the computational bound that is meaningful for us to live with, and what is the small probability of success that is meaningful for us to live with, and then consider security in that sense. Okay, so while all that we saw so far is useful, this is not actually what gets applied out there because of sort of the limitations of perfect secrecy that I talked about. Okay, any questions here? Okay, so we will call this the computational security. Like I said, we will be sort of in this setting of computational security. Okay, so where we will consider only efficient adversaries. Okay, and allow a small probability of success for the adversary. Okay, so precisely how this is done, again we will formalize what these things are. formalize what efficient means and formalize what small means. There are two approaches to take here when we define computational security, and both are reasonable approaches, but I will focus on one today, which is the asymptotic approach. But I will just spend a couple of minutes to talk about the differences between them. So in the concrete approach, you state concretely what efficiency means to you, right? So maybe concretely what efficiency means to you is that somebody who is running a supercomputer with this power for 10 years will not be able to break my scheme except with probability half plus epsilon for a precise epsilon. Okay, so that is what the concrete approach could tell you. But what we will follow today, and again depending on sort of the textbook you read, some of them follow concrete, some of them follow asymptotic. This book follows the asymptotic approach. So in the asymptotic approach, you will have something called the security parameter. Okay, so security parameter n say. So this n essentially parameterizes security of the scheme. And what this means is that for varying n, you would essentially be considering varying adversaries, varying success probability. For instance, you could even think of the key length for possibly as a security parameter n. Okay, so then what this would mean, right, is that you will consider efficiency to be an adversary that runs in probabilistic polynomial time in n. So this is a term that we will come across frequently today, right. So here efficiency in the asymptotic approach would imply adversaries running in probabilistic polynomial time in n. So what does this mean? So polynomial time, so essentially an adversary is an algorithm. Okay, so when we say polynomial time, we mean that, so consider the input length of that algorithm. The adversary, so the algorithm when it runs in polynomial time, it runs in polynomial time in its input length. So the adversary will take in the security parameter as its input and will run in time polynomial in that input. Probabilistic essentially implies that the adversary can make randomized choices. Okay, so here in the asymptotic approach, instead of considering computationally unbounded adversaries, we will consider adversaries that are efficient, where efficiency implies that it runs in probabilistic polynomial time in the security parameter that we have, that is n. Okay, so essentially say today we have the key length say to be 128, and then we will consider adversaries that run in probabilistic polynomial time in that parameter. But maybe like tomorrow we can change the key length to 256 and then meaningfully still consider adversaries that run in time in that parameter, right. Whereas in the concrete approach, if you have considered the security analysis with a supercomputer that is present today and that you are only running for 10 years, tomorrow if you want to change to consider a different adversary, you now have to essentially recompute your calculation. Whereas when you have this asymptotic approach and the security parameter n, that is sort of inherent. You are essentially just changing the parameter to describe exactly what adversaries you are considering. Okay, and small would imply something that is called negligible probability, and I will define it formally, but I will encourage you to take a look at some of the examples to understand precisely what is negligible and what is not. Okay, right. So negligible, so essentially informally, right, a negligible function is one that is asymptotically smaller than any inverse polynomial function. Okay, I will formally define this, but I will not spend a lot of time discussing this definition, it's sufficient for you to understand this bit informally for the purposes of today, but I encourage you to take a look at it later. So a function f from the natural numbers to the non-negative real numbers is negligible if for every positive polynomial p there is an n such that for all integers little n greater than n, it holds that f of n is less than 1 over p of n. Okay, so for instance, the functions 2 to the minus n is negligible. Okay, so this negligible function is one that is asymptotically smaller than any inverse polynomial function, and for instance 2 to the minus n is negligible, right. So formally a function is negligible if for every positive polynomial p there is an n such that beyond that n f of n is less than 1 over p of n, right. So p is a positive polynomial. Okay, and really the advantage of working with negligible functions is the following, right, because negligible functions satisfies these properties. So let negl 1 and negl 2 be two negligible functions. So then the function negl 1 plus negl 2, right, of n is also negligible, and for any positive polynomial p, the function p of n times negligible of n is also negligible. Okay, so for today, maybe I will say it is sufficient for you to know that this is true, that 2 to the minus n is a negligible function, and these properties hold, that when you add two negligible functions, the resulting function is also negligible, and a negligible function multiplied with a positive polynomial function also results in a negligible function. Okay, so these are mostly the properties that we will use, and I will then ask you to spend some more time to get comfortable with the mathematical notion of negligible functions, right. So really the reason why I define this is again to overcome the limitations of perfect secrecy. We have to come up with some relaxations, and we will relax in terms of the adversaries that we would consider, which is now probabilistic polynomial time adversaries, and then we will relax the notion of success probability for the adversary. We will now allow the adversary to succeed with probability half plus negligible in the security parameter. Okay. Again, in this approach you could maybe consider different notions of efficiency and different notions of small success probability, and that is okay, that is not inherently wrong. We consider these just for sort of the advantages that come with it. For instance, negligible functions satisfy these properties, so it makes it easier for us to perform a probabilistic analysis, right. So, and similarly considering probabilistic polynomial time implies that we do not really have to consider the underlying model of computation. Okay, so that is really why we consider efficient adversaries in this sense. Okay, so I am just setting this up to be able to talk about computational security in a bit more detail. So any questions here? Okay, so then you will get familiar with this as we go on today, but let me again now let's consider the same setting that we were talking about before, right? So the setting we were talking about before was the following. So maybe I'll leave this here, right? We considered a sender and a receiver, each had a key k. The sender obtained the encryption of the message M under key k by running the encryption algorithm of pi and sends C to the receiver, and the receiver decrypts the C under key k to obtain a message M. Okay, and we were considering adversaries that can eavesdrop only the single ciphertext C. Okay, and we were considering this setting in the perfect secrecy notion, where we considered essentially computationally unbounded adversary. So there was no restriction on the adversary, and we required that the adversary should not be able to say anything about the message M that it could not have said prior to the observation of the ciphertext C. Okay, so now in the computational setting, how would we relax it? Okay, so we can consider the adversarial indistinguishability experiment similar to what we considered even in the perfect secrecy setting or perfect indistinguishability setting. So actually more formally I need to even reintroduce the syntax of private key encryption so that I parameterize it with the security parameter n. But since that will take us a bit of time, I am not going to do it right now, and I will do it as required. So I will just directly go to the security definition. So consider again the adversarial indistinguishability experiment. Okay, so similar to what we discussed last time, again we are in the private key setting, so that hasn't changed. So it's still priv k. Again we are considering an eavesdropper that eavesdrops only a single ciphertext, so it's still the same superscript EAV. We will consider it with respect to an adversary A and with respect to some encryption scheme pi. The difference now will be this will be parameterized with the security parameter n. Okay, and essentially this n will determine sort of how will parameterize both sort of the encryption algorithm and the decryption algorithm, the key generation algorithm, and also parameterize sort of the adversaries that we are considering and their success probability. Okay, so in the computational security setting, this is how the experiment would be defined. So the adversary is now given the security parameter. Okay, so essentially the security parameter is still n. 1 to the n is just writing n in unary. Okay, and the reason we are doing this again is just for technical reasons. You can ignore it if that is confusing at this point. The technical reason is that I described polynomial time algorithms are as those that run in time that is the length of its input, and essentially when it's unary, the length of the input is essentially going to be the security parameter. So that is why we write it in this form, but you don't have to worry about it. The adversary is given the security parameter is sufficient for you to understand. Okay, so the adversary is given 1 to the n and outputs a pair of messages M0, M1 such that their lengths are equal. Okay, again a key k is generated by running the key generation algorithm. Okay, now the key generation algorithm will also be parameterized with the security parameter. So for instance, this n might determine the length of the key that is output by the key generation algorithm. So again, in the previous instance, there was no security parameter. So whereas here, the security parameter might say determine the key length output by gen. Okay, so that key is generated by running gen on input 1 to the n, and again a uniform bit b in 0 1 is chosen. The ciphertext C is again computed as the encryption of MB under the key K. Again we refer to C as a challenge ciphertext. Again similar to what we saw earlier, A outputs a bit B prime, which is its guess for B, right, which is its guess for whether C corresponds to the encryption of M0 or M1. Okay, and similar to last time, the output of the experiment is 1 if A guesses correctly, right. So the output of the experiment is 1 if B prime equals B and 0 otherwise. Right, and so if similar to last time, if priv k EAV a comma pi of n is 1, we say the adversary succeeds. Okay, so this is the experiment. Are there any questions on the definition of the experiment? So in terms of sort of the underlying idea, everything is similar to what you had seen before, apart from the fact that there is a security parameter that's coming in, that's parameterizing the experiment, that is given to the adversary and that is used in the key generation algorithm. The only other sort of point is that we are restricting the adversary here to output 2 messages that are of equal length. This is really because, security in this sense where all information about the plain text length is hidden is impossible. So that is why we require this here. And if you are interested, you can take a look at some of the discussion there later. I will not discuss it today. Okay, but otherwise, at least the high level pattern should be very similar, should be reminiscent to what we talked about before the break. Right. So then the question is, how is sort of this notion of efficiency, efficient adversaries and small probability of success coming in, right? And we will see that in the definition. Okay, so a private key encryption scheme pi consisting of gen, enc and dec has indistinguishable, so this is the definition, or at least the name of the security definition in this context, has indistinguishable encryptions. So maybe so that I have some place to write on the board, I'll just call this EAV secure, right. So it is either EAV secure or has indistinguishable encryptions in the presence of an eavesdropper if for all probabilistic polynomial time adversaries A there is a negligible function such that probability priv k EAV a comma pi of n is 1 is at most half plus negligible of n. Okay, so again we are talking with respect to this experiment. So this is similar to what we saw last time, but we are defining security, right? So we are calling a scheme EAV secure. So private key encryption scheme pi consisting of gen, enc and dec algorithms is EAV secure if for all probabilistic polynomial time adversaries, right? So in the previous definition that we saw, we said every adversary A. So there was no restriction on the adversary, it could have been computationally unbounded, whereas here we are only considering some notion of efficient adversaries where efficient is captured by this probabilistic polynomial time, right? So a scheme pi is EAV secure if for all probabilistic polynomial time adversaries A, there is a negligible function such that the probability with which the adversary A succeeds in this experiment is at most half plus that negligible function. Okay, so this is the other relaxation that is coming in, where we are allowing the adversary some small probability of success, that we can live with. Okay, so for instance, I mentioned 2 to the minus n is a negligible function in n. So if you consider say n to be 128, 2 to the minus 128 is a really like small number. You might be hit by lightning twice before you hit that probability of success. So it is a reasonable relaxation for us to consider. Okay, so this is how we will define things in the computational security notion, right? So we are considering some efficient adversaries and we are allowing that efficient adversary some small probability of success. Okay, so it's the difference between the definition of security in the perfect indistinguishability setting and the definition of security in the computational indistinguishability setting clear? So again notice we are still allowing the adversary to only still observe a single ciphertext C. So that hasn't yet changed. What has changed only is this computational relaxations that we are allowing. So any questions here? Okay, so oh, it's 12:50. Until how long can I go? 1. Okay. Sorry? 1 is fine. Okay. Okay, so so because we only have 1 day, I will not discuss EAV secure encryption scheme, right? So we saw a perfectly secret encryption scheme, that's the one-time pad. There's something called a pseudo one-time pad. The name is not as popular, but essentially you can build it with a stream cipher if you've heard of it, or a pseudo random generator, and with the same idea that we had for the one-time pad, we could build a scheme that is EAV secure. Okay, but I will not discuss that scheme today in the interest of time. So if somebody is interested in taking a look at it, take a look at the textbook or come talk to me afterward. So instead what I will now do is discuss a different adversarial attack strategy, right, or attack setting, where here essentially, right, so for this EAV secure, the pseudo one-time pad, the one-time pad encrypted by taking m XOR k, where the key k was of the same length of the message m. A scheme that is EAV secure will operate similarly, but instead will use an algorithm G, which takes the key as the input, where this G with some small amount of true randomness, that is the key k, is able to sort of expand this to output a string that is pseudo random, that looks like random, and essentially so now it allows you to expand up to say the message length. So we are no longer having sort of the limitation that we had in the perfect secrecy setting, and this structure where G satisfies the property of being a pseudo random generator, which I have not defined, will lead to something that is EAV secure. Okay, so this is just sort of a hint or intuition as to how you can build these schemes, but I will not focus any more on this definition, and I will focus on something that's related to chosen plain text attacks. Okay, so any questions? G? So okay, so right, so this was the OTP, right, the pseudo one-time pad. okay, essentially following the same idea as the pseudo one-time pad, but instead of XORing M with the key k, you XOR M with G of k, okay, where this G you can think of as an algorithm that takes in say n bits of randomness, okay, which is the key k, and then outputs some L bits that look close to random.
And then you can reuse the same key to generate.
Good question. No. So actually, the only so it's in EAV security. Again, if you see, we are only allowing the adversary to eavesdrop a single ciphertext. It's still not the setting where you can eavesdrop multiple ciphertexts. So it satisfies EAV security. So it satisfies security when only one ciphertext is observed. When two is observed, it does not satisfy security. But what it does overcome is that the key is no longer required to be the same length of the message. The key can now be shorter, right? So that is what it
There is a seed value.
exactly. So yeah, exactly. It's a seed value. So if you come across stream ciphers, maybe some of you, pseudo-random generators you can think of as sort of the or to put it differently, stream ciphers are sort of the practical instantiation of what we hope pseudo-random generators to achieve. Okay, so but I will not discuss it formally at all. I've only discussed it informally. Don't worry about it if this discussion, like went over your head. I'm not going to go there today. So instead, what I want to spend time on before we break for lunch is motivate CPA security. Right, so CPA security, where CPA stands for chosen plain text attacks, is the following setting. So here again we have a sender and a receiver, but and the sender sends some ciphertext C to the receiver. The adversary is still trying to figure out what the underlying message of the ciphertext C is, say, but in addition, the adversary can request, say, some messages M1, receive C1, that's the encryption of M1, request M2 and receive C2, that's the encryption of M2, and so on and so forth. Right. So essentially, the adversary can choose some plain text of its choice, right? So some M1 through MT, receive ciphertext that it knows corresponds to those plain texts, but still, even after having this C1 through CT information, when it observes a ciphertext C for which it does not know its underlying message, it should not be able to figure out with probability better than say half plus negligible if that underlying message was M0 or M1. So this is the chosen plain text attack notion, and I mean it's practically motivated, right? So for instance, maybe there is a terminal that is publicly accessible. So you use a terminal to send some message to your friend. You see what the ciphertext you obtain when you want to send a message. Now, when your friend is sending that message, or another friend, maybe your enemy is sending another message, you can only observe what's being sent across the channel, but you don't know exactly what the underlying message is. But even though you have sent some messages and you have seen those ciphertexts, when you see a new ciphertext, you should not be able to tell what the underlying message is. So essentially, chosen plain text attacks capture such security. Okay, and so for instance, the eavesdropping security that we talked about is a very, very basic form of security, and in fact, modern encryption schemes should satisfy not only CPA but something called CCA, which is chosen ciphertext attacks. We'll come to that later in the day. But this is what CPA security is, right? So essentially, the adversary maybe has knowledge of some C1 through say CT, and then is observing some C. So it also knows C1 corresponds to the ciphertext of M1, C, and etc. up to CT, and is still observing some C and should not be able to tell what the underlying message of C is. Okay, so this is chosen plain text attack. So informally, is the setting clear?
Yes.
Okay, so then let us formalize chosen plain text attacks, right? So similar to what we have done so far, we will again formalize it using an experiment. Okay, so here in this experiment, we will call this the CPA indistinguishability experiment, and now this would be priv k CPA a comma pi of n. So again we are in the private key setting, but we are now considering chosen plain text attack, so the superscript has changed to reflect that. For an adversary A against an encryption scheme pi with the security parameter n. Okay, so that's why it's priv k CPA a comma pi of n. So okay, so consider the following experiment for an encryption scheme pi, adversary A and value n for the security parameter. So now a key k is generated by running the key generation algorithm of pi on the security parameter 1 to the n. The adversary A is given input 1 to the n and oracle access to enc k. So I will explain what this is, right? So we want to model chosen plain text attacks, right? So essentially what we want to model is what I described here, that the adversary can send a message M1 and then receive C1, that is the encryption of M1. So in order for the adversary, so can the adversary compute C1 on its own? So why no? Exactly, right? So the adversary cannot compute the ciphertext on its own for chosen plaintext of its choice because the adversary doesn't have the key. The key k is kept secret. So how we will actually model this is we will consider some encryption oracle. Okay, so there is some oracle in the sky, right? That oracle is keyed with the key k that is generated by running the key generation algorithm. The adversary will submit plaintext of its choice to the oracle and receive ciphertexts that are the encryption of these plaintexts. Okay, so this is how we will model chosen plaintext attacks theoretically. Okay, so as I mentioned, there are attacks that can be carried out in practice, right? And we will have to theoretically model them to analyze security under those attacks. And we will theoretically model an adversary that can have the capability to perform chosen plaintext attacks by using something called this encryption oracle. Okay, so the adversary in this CPA experiment will be given the security parameter and oracle access to this encryption oracle. Okay, to this encryption oracle, A can submit plaintext and receive ciphertext of its choice. Okay, so is the notion of the encryption oracle clear? Okay, so now after oracle access to NK, A outputs a pair of messages M0, M1 of the same length. Then a uniform bit B in 0, 1 is chosen, and then a ciphertext C is computed as the encryption of MB under key K. So this bit is similar to what we saw before, right? So uniform bit B is chosen and either M0 or M1 is encrypted according to whether B was 0 or 1. So this ciphertext is computed and given to A. The adversary continues to have oracle access to the encryption oracle. And then outputs a bit B prime, which is its guess for B. Okay, and similar to before, the output of the experiment is defined to be 1 if B prime equals B and 0 otherwise. Okay, and if the output is 1, we say that A succeeds. So I'll come to the definitional bit in a second. But what you can see is the following, right? So in the CPA experiment, a key K is generated. The adversary A is given the security parameter as input, and sort of in order to capture the CPA notion, also has oracle access to an encryption oracle to whom it can submit plain text and receive ciphertext. And then again the adversary outputs a pair of messages M0 and M1. And similar to before, a uniform bit B is chosen, and either M0 or M1 is encrypted depending on what B is, and that resultant challenge ciphertext is given to A, right. Again the adversary A here continues to have encryption oracle access and then outputs a guess for the bit B, it's guess B prime, and similar to before the output of the experiment is 1 if B prime equals B and 0 otherwise. Okay, so really sort of the new thing here is the fact that the adversary has oracle access, and this is done in order to capture that the adversary is no longer just an eavesdropping adversary that is eavesdropping a single ciphertext, but it's an adversary that can perform chosen plain text attacks. Okay, so is the experiment clear? So then I don't want to take too much more time, but let me just finish the definition. Okay, so a private key encryption scheme pi is CPA secure, so or has security under chosen plain text attacks if for all probabilistic polynomial time adversaries A, there is a negligible function such that the probability with which adversary A can succeed in the experiment priv k CPA A comma pi of n is at most half plus negligible. Okay, so essentially we have changed how we consider the experiment by allowing chosen plain text attacks, and now a security definition follows a very similar pattern where for CPA security we are again in the computational setting where we are considering efficient adversaries, where by efficient we mean PPT adversaries, probabilistic polynomial time adversaries, and we still allow a small probability of success via the negligible function. But now we consider the security to be the probability with which the adversary succeeds in the priv k CPA A comma pi experiment. Okay, so this is the notion of CPA security. So I'll just leave it up there for a minute. You can ask me if there are any questions. How we will achieve CPA secure schemes using a tool called pseudo-random functions, that is what is modeled by block ciphers in the real world. Okay, so we will break now and then take a look at it.